All right, hello. Welcome back. 12.1, even more about regression. Uh, Last couple days we've been working on linear regression of the type y hat equals a plus bx. Hopefully you're remembering that hat's a prediction. Remember, hats are predictions. A, your expected or predicted or your average value of the y variable when x is 0, and B, your average increase in y for every increase in 1 on x. Good stuff, all in the background. Today we're doing more about regression. We're doing inference on linear regression. Specifically, we're doing inference on beta, where beta is the true slope. Remember, we don't know the actual linear relationship between these x and y variables. We just have an estimate of it. Our estimate is b. B is going to be used to estimate beta. So we're finding b's. We use those as our best estimate for beta, the true slope, and we're going to do some inference on beta from that point estimate. So sampling distribution of b. Why are we showing you this? The idea, as always, is that different samples are going to give different estimates of beta. The three above examples also slightly different slopes, slightly different intercepts. Not surprisingly, different samples are going to give you different estimates for that true slope. We're not going to need to do a sampling distribution quite the same detail we did as Chapter 7 for mu's and p's, that is sampling distributions of x bars and sampling distributions of p hats. But we are going to say just generally that b is going to be distributed approximately normally with a mean of the true slope and a standard deviation that I'm not really going to concern ourselves with. I'm just going to call it sigma b hat. I'm not going to tell you where it comes from. It's not important. We are not going to do detailed calculations for the sampling distributions of b like we did for x bar and p hat. But the big idea, though, is that these statistics from our sample, these these slopes here from our sample, they are distributed normally. So we're going to be able to do the same kind of inference, creating confidence intervals and performing significance testing like we had in the past. So it's conditions to do this sort of regression inference, that is, inference on beta, the true slope. All this is going to be for the true slope beta. We could do inference for the true intercept alpha, but it's not, we're not going to cover it in this class. It's beyond the scope, and it's not that interesting comparatively. So we've got 5 conditions. These are the most conditions we've got in order to perform these inference procedures. And these 5 conditions are given by this liner mnemonic, L-I-N-E-R, where L is linearity. We need to see a linear relationship. The true relationship is linear. So we need a linear relationship. We're going to tell that probably from a scatter plot, seeing that, yeah, it does look kind of linear to me indeed. Independence is easy. Normality, we're going to be looking for, well, we'll show you in a moment how we check this normality condition, but it's going to be normality for any fixed value of x. The response y varies according to a normal distribution. We'll get to that in a moment. Equal variance, that's an interesting one. That's kind of like equal spread at all x values. Obviously, there's going to be a spread around the true value, around the least squares regression line. We'd like there to be an equal spread at each x value. We'll show you what that looks like in a moment. And then randomization, that's obviously coming from a randomized experiment or a random sample. How do we check these things? Well, first you're thinking, man, there's a lot of conditions to check, Mr. Kraviec. The good news is that the plots to check liner will usually be given. The reason for that is it just takes too dang long to make all the plots we're going to need to check these liner conditions. So usually they'll just give them to you, and you'll have to look at the graphs and say, yes, this condition is met because blah, or no, this condition is not met because blah. So exciting times. The linear condition. We are going to need to see that the residuals are centered at residual equals 0. We're going to need to see the overall pattern is roughly linear. Okay, so we're going to need that. We don't want a curved pattern on the residual plot. That would be bad. We don't want to see that. That would tell us that a linear model is not appropriate. Take a look at yesterday's example where we saw a curved residual plot suggesting a quadratic regression or some sort of polynomial regression of order greater than 1 would be appropriate. Independence, as always, 10% condition, or one doesn't have to do with the other. Normality, we're going to look at a stem plot or a histogram or an NP plot of the residuals. And what we're going to see, we're going to need to see something that has minimal skewness and no other major departures from normality. So skewness or significant outliers or a clear, goofy shape, that would say it's not normal. Equal variance, I'll show you what that looks like in a moment. The amount of scatter should be roughly the same from the smallest to the largest x's, and then random's the easy one. But you can see there's three checks here that are going to require a plot. Of some sample data. So that's a lot of work. The good news is you won't actually have to do that work. They'll give you those plots. Like in this example right here, we have 4 plots here. This is a scatter plot of x versus y. This is a residual plot with our residuals on the y-axis and our x values on the x-axis, obviously. This one is a histogram of residuals, and this one is an NP plot. Recall, NP is normal probability. If we have a linear normal probability plot, that suggests the data is distributed approximately normally. So that's an NP plot of your residuals there. So in checking those liner conditions, the L condition, the linear condition, I would say the scatter plot is approximately linear, and the residuals show no clear pattern. So yeah, that seems, scatter plot seems to be approximately linear. I'm looking at that one for that, and the residuals show no clear pattern. I'm looking there, and that looks good to me. Independence condition. These helicopters don't affect each other. So we're probably good on that one. Nothing to check there, just need to see, yeah, we're dropping helicopters, so they should be fine. Normality. You can look at a couple things there. The one we're most used to is probably going to be that histogram. What we're going to see here is that the histogram of residuals is approximately normal. What am I talking about there? Histogram of the residuals. I'd be talking about that guy right there. And that's a very normal looking histogram. That thing looks really nice, almost suspiciously nice. So we have linearity, we have independence, we have normality. Equal variance. That's the one that's a little interesting here. Equal variance. Remember, variance, that's spread, variability, deviations around the prediction equation, that kind of thing. When we're looking at equal variance, we want to look at the residual plot. And here it shows approximately equal variance at all values of x. And what am I talking about there? I'm looking at, somebody's red here. Looking at this guy, but specifically I'm looking at this kind of envelope of residual values. So it seems to be about equal variance, about that residual equals 0 there. So it seems to be going up about the same amount as it goes down for each different x value. So that's equal variance. That one's a little goofy. And our last condition here is randomness. As always, there's no way to check that. We must assume, or it must be given, as always. So those liner conditions, again, you don't have time to make those plots. That's like 5 minutes worth of plot making. You just don't have time to do it. So oftentimes those plots are going to be given to you, and you're going to have to interpret them as we have done here. So let's see. Anything else I need to look at here? So next thing we're going to be doing is estimating the parameters. And if you haven't figured out, when we see that word estimating, we need to be thinking confidence interval. So we'll be needing to do that, and we'll pick up that on the next page. We're just going to have a couple examples here today. We're going to be doing one confidence interval for beta, the true slope, and one significance test for beta. So let's do it. First one, constructing a confidence interval for the slope. Your formula, as always, is given right here. B plus or minus t star, standard error of B. The good news, B and the standard error of B will always be given by the computer output. So that's happy days. The only thing we're going to have to find is t. The goofy thing about t, or t star rather, is that the degrees of freedom here is n minus 2. And that's the only case where degrees of freedom is not n minus 1. Here it's n minus 2. It's the most frequently missed thing on this stuff. Just as a reminder, our general confidence interval formula is statistic plus or minus our critical value times the standard deviation of that statistic. Here the statistic is B, the critical value T star, standard deviation of the statistic, standard error of B. So two of those values are going to be given to you. One of them you're going to have to look up on the table. That one you're going to have to look up is the T star critical value. So we're over here doing an example of flight time versus drop height. This is from an example that if we hadn't had 10 snow days, we might have done in class, dropping some paper airplanes, seeing how long it takes them to hit the ground, dropping them from different heights. Okay. Write the LSRL, that is the least squares regression line, and define the variables, and then construct and interpret a 95% confidence over the slope of the population regression line. One thing I neglected to do up here was to name the test. You can call it a t-interval for the slope or a t-interval for beta, the true slope of the least squares regression line. Now, they're not super picky about it. It's still, in practice, a t-interval, like every other t-interval we've calculated. Recall that t intervals are generally going to be a little wider than z intervals as we're estimating the standard deviation of the statistic based on some sample data. Remember, whenever we use sample data for our estimates of standard deviation, we're generally going to need a t interval for that. So let's do it. Mr. Rose's class, I should change her name in here. We checked the conditions already. That's good news. We can just say that in the plan step, make our lives easy. So A, write the LSR line and define the variables. Okay, so you should be able to do this. Pause it for a moment and write it. But you should have negative 0.03761 plus 0.0057244x, where x is the drop height, and y hat, always putting a hat on that y, and remembering that hats mean prediction, predicted, what is it, flight time. Great. You might think it's a little odd that we would be using a linear model to predict flight time from drop height. You might be saying, Mr. Kraviec, seems like a quadratic model would be more appropriate. Yeah, you're probably right, but over this small of a time span, the linear approximation is probably going to get us there. I don't disagree with you, though. Those of you who've taken AP Physics should know that our time equation should have a squared term in there somewhere, I'd expect. So we're going to go ahead and construct an interval. So we're going to do B. We're going to state, plan, do, and conclude, but the good news is the plan step, the longest step, the checking the conditions step, is met for us. So happy days. Let me scoot right there. Okay. So part B. First, we're going to state, we're going to construct a 95% CI for beta, where beta is the true slope of the LSR line of flight time versus drop height. State step's easy. Just define your parameter. We're doing the same thing in every state step, defining our parameter. Our plan step. All we have to say here, we're constructing a t interval for beta. Easy peasy. State plan we can go ahead and do now. So we're going to need to use that formula from above. That is going to be B plus or minus T star n minus 2 times the standard error of B. We have 2 of those values, as I said, so let's draw some lines here. Ooh, yeah, I can just barely fit it. So here is our B value right here. Here is our standard error of B right there. So we're going to use those 2 values, so I can plug those in right away. The other one's going to be a little interesting where that comes from. So again, that's, oh, I've got it right there. So it's going to be 0.0057, what is it? 244. That's going to be right there in the middle of our interval. That's the sample slope that we calculated from the data we had. Plus or minus some critical value, which we'll find in a moment, times the standard error of B, which is also given. Whoops, moving stuff around. Oh God, what happened? There we go. So, 0.0002018. Okay. All right. So let's go ahead and find that T statistic, that critical value T statistic. We're going to go ahead and open up our AP formula sheet. Ever so slowly. Hey, there it is. Sweet. So maybe it'll load for me. Spinning wheel. Spinning wheel. Spinning wheel. All right, looks like we've loaded here. So let's take a look at our T-star critical values. You'll recall, perhaps you'll recall, that our degrees of freedom here is n minus 2. We had 70 observations on this problem, as you recall. So that's 70 minus 2 is 68. But we don't have 68 on here. We have 80 and 60. So that means we're going to have to use the 61. And then we will go ahead and 95% confidence, find where they intersect. Happens to be a very clean looking T-star critical value. It is 2 on the nose, 2.000. It doesn't always come out that nicely. Here it does. So it's 2.000. So our critical, or our interval then is 0.0057244. Normally I couldn't do that in my head. I can double that number though, plus or minus 0.0004036. And then adding and subtracting that 4036, we're going to get, do I want to try this one in my head? Dangerous times here. 0.0053208, I think. And top side 0.00. What are we going to do? 61. 280. I think that's right. Check my math. Did that in my head. Might be wrong. Been wrong before. Let's go back to full screen. So we've done that. All we need to do from there, assuming that I did my algebra correctly, is conclude. That is, we are 95% confident that the true, excuse me, again, that the interval, write the interval again, 0.0053208, comma, 0.0061280, captures the true value of the slope of the LSR line. Make sure we have some context in there, as always. Drop time, or I guess flight time versus drop height. Same sort of interpretations we've always used. Shouldn't change there. All right. We're going to skip that example. If you want to do it, you can. I think this example is in the book if you'd like to check your work on it. Last thing I want to look at is performing a significance test. That is a t-test for a slope or a t-test for beta. So again, we're assuming the null hypothesis is true. Generally, the null hypothesis on these is going to be that the null hypothesis, beta equals 0, is going to be typically our null hypothesis. That is, if beta is 0, that means there's no association. And our default ha is going to be B not equal to 0, that is, there is an association. So those are our default hypotheses. And the good news is that computer output already has the results of those default hypotheses. And I'll show you that here just in a moment. But as always, that test statistic, for that t-value for these is going to come from the slope we observe minus the hypothesized value. Here, the hypothesized value is generally going to be 0 over the standard error of B. And again, the good news here, both of these are going to be on your your computer output. In fact, the p-value is as well, but I'll show you that in a moment. Still having degrees of freedom n minus 2. Still calculating or interpreting p-values just as we always have. Recall, we interpret p-values, the probability of observing a test statistic this extreme or more extreme given the null hypothesis is true. So if there really was no association, if the true slope really was 0, what's the probability that we get a result this far away from 0 or further? So here we go. Infants who cry easily may be more easily stimulated than others. Might be a sign of high IQ. Great. Child development research has explored the relationship between crying of infants 4 to 10 days old and their later IQ. We snapped some rubber bands on the soles of the feet of these babies, made them cry. Counted how long they cried for. We later measured their IQ, and we got this nice little scatter plot. So let's do a test here. A scatter plot, and then Minitab data output for the data show a random sample of 38. Again, that's your n value. Do these data give convincing evidence that there is a positive linear relationship between crying counts and IQ? Assume conditions have been met. All right, so we're going to have an alternative, aha, of beta greater than 0. So we'll see how that ties back into things. So, state plan. Do conclude. State. We're interested in beta, the true slope of LSR line of cry count versus IQ. And the ho, beta equals 0, that is, there is no association. The ha, beta greater than 0, that is, there's a positive association. Okay. That's all you need. That's all you got to have for your state step. Our plan step is even shorter since we've been told the conditions are met. We're going to perform a t-test for beta. And we were told that conditions are met. Oh, happy day. Great. The do step we can do a couple different ways, and I'll show you both ways. We could calculate the t statistic. It would be the observed beta minus the hypothesized value over the standard error of B. So again, there's your B. There's your standard error of B. Okay. So our t statistic is going to be here. 3.07, excuse me, not 3.07, check that. 1.4929 divided by 0.4870, which is 3.07. What do you notice if you're a clever student paying attention? 3.07 is right there. They've already found your t statistic for you. What else might you notice? Well, here's a p-value. But the thing is, this is the p-value for the ha, where the ha would be beta not equal to 0. So recall what that means. If it's not equal to, we're looking at that far away in either direction. 3.07, negative 3.07. But since we've only got a one-sided alternative, our p-value is actually going to be half of that area. Since we're only looking at the greater than, we're only interested in this area. So the p-value will be half of that value, should be 0.002. Where else could we see that? Well, let's take a look at our t-table. Go ahead and look at your t-table. We had 38 infants, so that's like 36 degrees of freedom. We'd be looking 30, we'd have to go to 30. We got a value of 3.07, so somewhere between these two values right here. So I should expect a p-value between these two. Since my test statistic was between these two values, my p-value should be between those as well. And that seems to match with the results from the computer output, just a little more specific there. So our p-value is 0.002. What do we conclude? Well, p-value that low. Since our p-value 0.002 less than any alpha we might have chosen, 0.05, we reject the whole. We have sufficient evidence to conclude. What are we going to conclude? That there's a positive linear relationship between crying counts and IQ in the population of infants. That is all we need to do for today. Understand that there's some more examples here. You don't need to do them. Those two examples are enough. You will have one of those two types of problems on your test. So make sure to do 12.1 homework. Hell, I'll just tell you, make sure you can construct a confidence interval with the state plan do conclude process. You'll have multiple choice questions over both, but your free response question will be over confidence intervals. So that's all you've got from me. Good luck and Godspeed the rest of the week. Your 12.2 lecture is recorded and on Schoology already. If you want to do that today, what's it going to hurt? Adios.